Imagine you run a small online shop. For every past order, you've recorded a few things: the city, the number of items, how the customer paid. Ask how many orders came back last year, and a database simply counts them. That answer is already stored. But now ask a sharper question: will this brand new order be returned? Nobody wrote that answer down. It has to be predicted from the patterns hiding in everything that came before. Learning to make that prediction is the whole of machine learning. Here is the mental picture we'll keep coming back to. Each dot is one example from the past, an input on this axis, and the answer we already know on that one. Instead of hand-coding a rule, the machine hunts for a function, a smooth curve that threads through the cloud and captures the trend. We write it f of x equals y. Feed in an input, get back a predicted answer. Learning means finding that curve from the data alone. And once we have it, prediction is easy. A fresh input we've never seen comes in. Read the curve at that spot, and out drops our best guess for its answer. So what does the data actually look like? Picture a spreadsheet. Every row is one example, one order, one patient, one photo. Every column is something we measured about it. The input columns, the ones we get to look at, are the features, and we gather them into a matrix we call capital X. Rows are examples. Columns are features. And sometimes there's one special column, the answer we're trying to predict. Was it returned? What did it sell for? That column is the label, or the target, written little y. Here's the leap that makes the whole subject visual. Take a single row. Its features are just numbers, and read those numbers as coordinates. The row becomes a point. A whole table of rows becomes a cloud of points in what we call feature space. Scatter every row this way, and the geometry does the teaching. A model learning from this data is really carving up feature space, deciding what each region means. Now the first big fork in the road. Does our data come with that answer column or not? If it does, we call it supervised learning. The known answers supervise the model as it trains. If it doesn't, it's unsupervised. The model gets only the features and has to find structure on its own. Let me show you the three pictures that cover almost everything. First, supervised learning splits in two. When the answer is a continuous number, a price, a temperature, that's regression, and the model fits a line or curve through the points to predict the value. When the answer is instead a category, spam or not spam, this disease or that one, it's classification. Now the model draws a boundary through feature space, carving it into regions, one per class. And with no labels at all, the classic move is clustering. The model finds groups purely from how the points sit. It never gets told. These are two kinds. It discovers the two blobs itself. That's the flavor of unsupervised learning. There's a fourth cousin worth naming: dimensionality reduction, squeezing many features down to a handful while keeping what matters, so you can see and compress your data. But regression, classification, and clustering are the three you'll meet first and most. Now, the single most important habit in the whole field. We don't just want a model that nails the data it already saw. Anyone can memorize the past. We want one that works on data it's never met. That skill has a name: generalization. And to measure it honestly, we split our examples in two before we start. Start with all our labeled examples in one cloud. Now split them. Most for training, the rest held back for testing. Say 70% to train, 30 to test. The blue points, the model is allowed to learn from. The gold points, we hide away and don't touch. Fit the model on the blue training points only. It learns its curve from those, never seeing the gold ones. Then the moment of truth. We bring back the gold test points and check how close the curve lands to their real answers. That gap, on data the model never trained on, is our honest estimate of how it'll do in the wild. Never, ever measure success on the very points you trained on. This next idea is the heart of the lesson, the trade-off that never goes away. Take the exact same data and fit it with three models of growing complexity. Watch what happens. On the left, a model that's too simple, a single straight line through a curvy cloud. It can't bend to follow the shape, so it misses badly, even on the training data. We call this underfitting, and the cause is high bias. In the middle, a model with just enough flexibility. It curves to follow the real trend without chasing every wobble. This is the sweet spot, a good fit that captures the pattern, and it'll generalize well. And on the right, a model that's far too flexible. It contorts itself to pass through every single training point exactly. Training error near zero. But look how wildly it swings between them. That's overfitting. It's memorized the noise, not the signal. High variance. Now plot the story as one graph. On the bottom, model complexity, growing left to right. On the side, error. Training error just keeps dropping. The more complex the model, the better it fits what it saw. But test error tells the truth. It falls at first, bottoms out at the sweet spot, then climbs again as the model starts memorizing. That gap opening up on the right is overfitting made visible. Read it in three zones. On the left, both errors high, underfitting. On the right, train low but test high, overfitting. And right where the test curve bottoms out sits the Goldilocks model. Complex enough, but no more. Finding that spot is what the next lessons are all about. So how does a model actually improve? Not in one shot, in a loop. And once you see the loop, every learning algorithm looks the same underneath. It begins with data, the examples. They flow into the model, which makes a prediction for each one. We compare each prediction to the true answer and measure how wrong it is. That number is the loss or the cost. A single score for how badly we're doing right now. Then the crucial step. We nudge the model's internal settings a little, in whatever direction makes that loss go down. And then we do it all again. Predict, measure, adjust, round and round. Each pass a bit less wrong than the last. That loop is learning. And this is exactly where two words come in that people mix up. The settings the loop tunes for you. Those are the parameters learned from data. The knobs you set before it starts, like how flexible the model may get. Those are hyperparameters chosen by you. Parameters are learned, hyperparameters are picked. Your turn. Here's a task. Predict a house's price from its size in square feet. Is that a regression problem or a classification problem? Pause for a moment, decide, and be ready to say why. I'll wait. Here's the reasoning. The key question is always, what kind of thing is the answer? Price isn't a category. It's a continuous number that can land anywhere. 2 lakh, 5 lakh, 17.3 lakh. Whenever the target is a number on a sliding scale, it's regression. And there's the picture. Size along the bottom, price up the side, a line fitting the upward trend. If instead we'd asked something like cheap, medium, or expensive, three fixed buckets, that would flip it to classification. Same houses, different question, different task. Trap 1, the very first check. Is there an answer column? If yes, it's supervised. If not, unsupervised. Get this backwards and nothing else lines up. Trap 2. Coding your classes as 0 and 1 doesn't make it regression. What matters is whether the target is a true continuous quantity or just a label wearing a number. Trap 3. The big one. A tiny training error can be a trap. A model that memorizes scores beautifully on what it saw and fails on everything new. Only the test set tells the truth. And trap 4. Don't touch the test set while building. If you keep tweaking until the test score looks good, you've secretly trained on it, and the number stops meaning anything. Let's tie it together. At its core, a model learns a function from X to Y, straight out of the examples. No rules handwritten. When the data carries labels, it's supervised. regression for continuous answers, classification for categories with no labels. It's unsupervised, clustering to find groups, and dimensionality reduction to compress. Always split your data. Train the model on one part and judge it on unseen test data, because generalization is the only thing that counts. And hold the great trade-off in your head. Too simple underfits with high bias, too complex overfits with high variance. The art is landing in between. Get these 5 ideas solid, and everything ahead in machine learning has a place to stand.